Now, the reality is that we oftentimes, in fact, most of the time, we don't actually know what the population mean is or what the population standard deviation is. Now, sometimes we're able to estimate the population standard deviation with a lot of certainty because we've been taking these samples for a very long time, such as if when we were doing those control charts back in chapter 7, we were taking samples over and over and over again for a very long period of time. So we know that, hey, the population standard deviation, while we don't know it, we know that it's really, 0.03 like it was in the serial example that we were working in the first video. But so a lot of times we can estimate it, but then again, a lot of times we don't know it. So if we don't know it, then we're going to use a sample deviation, the sample standard deviation, which is S, and we're going to use that in place of in the z-score. But since we can't really calculate a z-score with the standard deviation, we're going to calculate something similar called a student's t-distribution or the t-distribution. And when we calculate the t-distribution, we're going to take, x bar minus mu, this is assuming we still know the population mean, and then we'll divide it by the sample standard deviation divided by the square root of n, but we have to have what we call degrees of freedom. So degrees of freedom is referring to the extent of the broadness of the tails. So the fewer degrees of freedom, the broader the tails, the more degrees of freedom, the smaller the tails are, the narrower the tails are. So we're still assuming that everything is normally distributed, which we can normally assume, remember, as long as our sample size is greater than 30 or the mean is normally distributed according to the central limit theorem. And in a t-distribution, we're going to have slightly broader tails because, again, we don't know the population standard deviation, so we're using the sample, which is already a little bit off. But we have to calculate, again, that degrees of freedom we call n minus 1. We calculate as n minus 1. So again, remember our t-distribution here, which t and then subscript df is the degrees of freedom, is still bell-shaped. It's still symmetric around 0. It still has those asymptotic tails, and I'm really sure I'm not saying that right, but which means remember that they get really, 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 really close to 0, but they don't actually touch 0. But we do have broader tails. And so as the degrees of freedom increase, the distribution becomes closer to the z distribution. So remember, degrees of freedom is sample size minus 1. So as we get larger samples, we more closely approach that z-score. So here we're looking at 3 different t-distributions. One has only 2 degrees of freedom, so that means a sample size of 3, remember. That would be the green line there. And notice how it on the tails, see how it is taller up here? It's higher, so we have broader, thicker tails here. When we have 5 degrees of freedom, which means we have a sample size of 6, then that's the blue line, and so here it's a little shorter. And then if we have 50 degrees of freedom, which means we have a sample size of 51, it's even lower. So again, the larger the sample, this is kind of our theme here, the larger the sample we can get, the better we are. So again, we do have t-tables. They're in your appendix right next to your z-tables, but they're not as comprehensive as a z-table. It only gives us some limited values, and it only calculates the upper tail of the distribution. We don't have a negative or a left tail of the distribution like we do with the z-score. So we're going to not really use the tables so much. You can, of course, if you'd like to, but we're going to use Excel to calculate this because Excel, and again, if you want to, the tables are on page 512 and 513 of your printed textbook. And you'll notice that they only go to 30 degrees of freedom, and you only have your margin of error is much smaller possibilities. Or actually, but they're just not quite as expansive. But we can use Excel to calculate these if we don't have a table value. So our formula is very similar to the formula that we looked at in the first video. We're going to calculate our confidence interval by saying X bar, the sample mean, plus or minus the t-score, so the t-distribution of alpha divided by 2, so the margin of error divided by 2, so we can split it in both tails with whatever, so many degrees of freedom, multiply by S, the sample standard deviation, divided by the square root of N. So again, very, very, very similar formula, except we're plugging in the t-distribution instead of the z-score, and we're using the sample standard deviation instead of the sigma, the population standard deviation. Now, this formula only works if X bar, if the sample mean, follows a normal distribution. Now, remember, according to the central limit theorem, if our sample size is larger than 30, we can safely assume that it does. If our sample size is less than 30, then we'll need to test to make sure that it really does follow that normal distribution. So let's go back to that introductory case where we were talking about the miles per gallon of the ultra green cars. So using the data that we were given earlier, which again is in your Excel spreadsheet for Chapter 8 on the worksheet titled MPG, let's construct a 90% confidence interval of the population mean. And I know our sample size is only 25, so it doesn't meet that central limit theory rule, but we're told to assume that the miles per gallon does follow a normal distribution. So we can go ahead and do that. Now, before we jump into that, I want to back up for just a second and let's talk about how we calculate this student's t-distribution just without using the table, how we calculate it in Excel. So we're really not using any data here. You can see I've just opened up a blank sheet. I just pressed this little plus button right here and opened up a blank sheet in my worksheet to we're going to calculate these t formulas because there's a lot of t-tests in Excel and I want to make sure that you're using the correct one. So let's just going with that data that we had before. Let's calculate the t-score or the t-distribution. Really, I should say t. Let's assume alpha, our margin of error is 5%, so we're looking at a 95% confidence interval, which means our margin of error is 0.025 in each tail. And let's use degrees of freedom. Let's calculate 2 degrees of freedom. Let's go back here. I don't want to do it that way. Let's calculate it with the 2 degrees of freedom that we looked at before. 5 degrees of freedom and 50 degrees of freedom. All right, so this is the data that we're going for here. Again, we're just calculating that t-score. So I'm going to go up here to formulas, and I'm going to choose statistical. Now I'm going to scroll down here, and I want you to notice there are a lot of t-scores. There's t-distribution and t-distribution two tails, and then there's t-distribution right tail, and then there's the t-inverse, and the t-inverse two tails, and then there's an actual t-test. So it may make logical sense of, hey, I'm calculating the t-distribution, I'm going to use the t-distribution test. But in Excel, that's actually not what we're wanting to calculate here. We're wanting to calculate the left tail, the inverse of the student's t-distribution. So we're not using the t.dist formula yet. We're going to use that later on, but not yet, not in this chapter. We're going to use the t inverse, okay? And I know that when you read, if you hover over it and it kind of gives you the description, it says, well, this is the left tail of the student's t-distribution, or here's the right tail of the student's t-distribution. That sounds like what I want to be using, but it's not. We actually want to use the t inverse, okay? So if I want to calculate the t inverse, remember the tables only calculate the right tail. The right tail. So my probability, remember, is going to be, if I have a 95% confidence, then that means I have 2.5% confidence in each tail. And since the table values, I'm basically showing you how to get the table values, is calculating the right tail only, that means I have to say 1 minus that. If I want to calculate just the left tail, I'll put 0.025 in here. But if I want to calculate the right tail, like the table is going to give us to get the table value, I'm going to say 1 minus 0.025, which is 0.975, okay? And then if I want 2 degrees of freedom, I'll plug in 2 there. And that gives me a table value of 4.3. Now I can just drag this formula down and I can go ahead and change my degrees of freedom to 5 and my degrees of freedom to 50. And this is how we get those table values. So if you're looking in your textbook on page 27 at example 8.4 and you're wondering how did they get those values, this is how we got them. You can look them up in the table, or we can calculate them in Excel using that t inverse formula. All right, so now let's jump over to our miles per gallon. So we're back to our case study here that we were looking at with the ultra green cars. Now there's lots of data that we need here, and you can calculate it all in one formula, or we can calculate it in parts and pieces. So first of all, we need to know, remember, we need the the sample mean. We need to know the t-score with, if it's a 90% confidence interval, then that means our margin of error is 10%, which means it's 5% in each tails. And our degrees of freedom, remember, is n-1. So if you remember, our sample size is 25. So that means our degrees of freedom is 24. Then we need to know the standard deviation of the population, or excuse me, the standard deviation of the sample, and then the square root of, well, our denominator is the square root of the sample size. So again, we can calculate those in parts and pieces, or we can calculate them all in one formula. So let's do it both ways. Let's calculate them in parts and pieces and then all in one formula. So I want to know the sample mean, first of all, and that's just going to be the average of all of these formulas, or all of these values, I should say, A2 through A26. And so I get the sample mean is 96.52, which if you remember from the first video, we went ahead and stated, and I told you then we'll come back and prove it. Okay, so next thing I want to know is my t-score, or my t-value, my t with 0.5 or 5% confidence, so 0.05, and degrees of freedom. So first of all, I got to calculate degrees of freedom. Remember, degrees of freedom is n-1. So let's go ahead and plug up here. N is 25. So degrees of freedom is the sample size of n minus 25. And that should be a lowercase n right there. There we go. Oh. D1 minus 1. Goodness, there we go, 24. So my t-value here, remember that's going to be that t dot inverse. Remember, it's calculating the right tail. So if I'm looking for what is the probability that there's 5% in the right tail, I've got to say 1 minus that, so my probability is 0.95, meaning there's 95% probability that everything falls to the left of that right tail. And my degrees of freedom, we just said were 24. So I get my t-score of 1.70882. Unfortunately, the t-scores always change because of those degrees of freedom, so you can't just memorize the 3 most common ones like we do with the z-score. And then I need the sample standard deviation, which is just, remember our formula, standard deviation, but I want it for the sample, so it's std.s of A2 through A26. So you can type them in here, or I'm gonna scroll and grab them. And that standard deviation then is 10.69704, blah, blah, blah. So our formula for the confidence interval, we've got the upper level and the lower level, or the upper limit and the lower limit, remember, is our mean. So for the upper, it's plus the t-score times, I'm going to open my parentheses, the sample standard deviation divided by the square root of the sample size, which is 25, close all my parentheses, and I get 100.18. So that's the upper limit of my miles per gallon. That's the upper limit of my confidence interval. And then the lower limit is the exact same score. So here's what the exact same formula, except I'm going to subtract instead of add. So here's what I'm going to do. I'm going to go back up here to this formula, and I'm going to press F4, which F4 adds those dollar signs, which makes it an absolute cell reference, so that when I drag the formula, it won't automatically change those cell references. So I'm going to add all of my cell references here with F4. Notice it didn't change the value. And now when I drag it, notice that all my cell references stayed the same. So now all I have to do is change this plus sign to a minus sign, and my lower limit is 92.85973. So we can say with 90% confidence, or 90% of the sample means fall between 92.9 miles per gallon and 100.2 miles per gallon. Okay, that's 90% will fall in there. So again, I told you this was where we calculated all of the parts and pieces separately and then put them all into one formula. What if we calculated the whole thing in one formula? This is very sophisticated Excel skills, but I know that we can do it. So I'm just going to move over one here. All right, so my formula, first of all, I need the sample mean. So I'm going to say average of, and I'm just going to type in here A2 through A26 because I know that's where all my sample data is. Plus, okay, now again, we're going to use minus for it's the lower limit, but I'm going to use plus for the upper limit. All right, here I want my T dot inverse formula with 0.95 probability because I'm estimating that there's 5% confidence in the right tail, so everything to the left of that right tail is 95%. Degrees of freedom is, I can go ahead and just type in 24 here, or I can use my cell reference there. If I wanted to, instead of using that cell reference, I could plug in the formula of 25 minus 1. Usually we don't have to use a formula for the degrees of freedom because it's just minus 1. All right, now multiply by the standard deviation of the sample for A2 through A26 divided by the square root of the sample size of 25, and boom, I get the exact same answer. And so again, if I make all of these be absolute cell references, I can drag it down, change the plus sign to a minus sign, and calculate the lower limit here. Oh, I put a 1 instead of a minus sign. There we go. So there we've got the exact same. So again, either way will work. As you get more comfortable with Excel and as you get more comfortable with the formulas, you'll probably find it's easier to just do it in one big formula like this. But to get started, it may make more sense to go through the parts and pieces in Excel and do them individually before you try to plug them all in one giant formula. Now, we did not go over in your textbook on page 272, there's example 8.6. It's about Massachusetts residents that are spending money on the lottery. And in fact, if you go over here in your Excel spreadsheet, you'll find that you have a tab or a worksheet for lottery. So we didn't go over this one together. I'm not going over it in the video, but I would encourage you to go over this one and by yourself, try it. Try calculating the confidence interval with a 95% confidence, and then check your answers against what the book shows. Again, that's example 8.6 on page 272. So this will give you just one more practice set before you get to your homework and your Excel simulation for this chapter.